guys, let me share with you my screen. So in today's class, we will talk about beam shear design. So far, we discussed in my class, we discussed the concept of shear resistance and how concrete develops shear resistance. And I think what I covered in the last class is I covered slab shear design. Slab shear design, okay? So in slabs, what we do is we don't add any stirrup. It's only our concrete. It should be able to resist the shear forces. And we went through the exercise, and we gave you a one numerical example. Now, today in class, we will cover beam shear design. But let me remind you, in concrete slab, so the shear capacity is developed by only one element, which is the uncracked concrete portion. So if you look at my screen, I'm going to zoom into the top right here. So we know that the shear crack will come at almost 45 degrees angle. And so this part here, it provides some resistance, but it's not reliable of the friction once the shear crack width increases, and also the doweling effect of those blue bars. We cannot count on it. So the only portion that we can count on it is this portion here, the portion of the concrete that is not cracked. Okay, so this portion provides some shear resistance. In beams, we get more than that. So in beams, we still have the same part, which is the uncracked portion of my section, in addition to something called shear reinforcement. Shear reinforcement on this side. So we have two things working together to create shear capacity for your beam. Most commonly, when I say shear reinforcement, most commonly it is called stirrups, but we have other options that we will discuss today. But when I share shear reinforcement, there are some options. The most common one is stirrups. Now, what happened is here, my equation before, when I talked about shear capacity, in slabs, there's only one component, which is concrete shear capacity. Today, when I'm talking about beams, you can see there's another term here, which is stirrup capacity. And then finally, your total capacity will be adding them together. Look at the equation. So the V sub R and V sub R is same as MR. So MR was the moment capacity. The V sub R is the shear capacity. And what does it mean, shear capacity? It means what is the maximum shear force that this beam can handle. It comes from two components. The first component is what concrete can take, how much concrete can take, in addition to how much my stirrup can take. Let me remind you the first part. So the first part is completely unchanged, which is VC. VC is concrete shear capacity. It's not going to change between slab and beam. Everything stays the same, no change. Let me remind you that phi C was our concrete resistance factor, 65%. Lambda is 1 for normal density. F prime C concrete compressive strength. And then D sub V is effective shear depth, which is the greater of or the maximum of two numbers, a 90% of the D and the 72% of the H. Okay? And then forget about walls. We're not designing walls in this course. And then the width of the beam is, give it letter B. Then finally, in this equation, everything is known except one guy here called beta. So beta, as I said, beta is a unitless. It is a portion or ratio of dV, which is how much still uncracked. It's a portion or ratio of dV. And so another thing here is called theta. And theta is, as the profiles, it looks on the profile, this is the angle of the crack. So guys, the last class we went very, very, very quickly. And we quickly found the beta for slabs. Because our slabs is always, we don't build like super thick slab, okay? Except it's a footing. Yes, for footing, yes, we make sometimes very thick footing. But for structure slab, like for floor slab, typically the 350 is a huge number. And for any slab below 350 millimeter thick, if you guys remember, the beta is 21%. 21%. And look up my screen. I said here more details in this lecture because you will see when we get to beta for beams. No, it is kind of a long story. We have to tell you the story from the start. Okay. So anyway, you will get more details about the beta today, but still theta is going to be the angle of the crack. Now, so you can see V sub C, which is concrete shear capacity, does not change. The same equation, no change. How about V sub S? What is V sub S? V sub S is the stir up capacity. Now, guys, let me show you. I'm gonna kind of split. So what I did here, you can see the same beam elevation in here, and what I did is I took the other part and I make it 3D. So this is a 3D of how your beam look like after you have shear crack. And you guys, you can see where is my stirrup in this picture here. Where is the stirrup? I'm asking you, is that stirrup? Yes or no?
No.
No, no.
The stirrup is here. So the
Yeah.
stirrup is oriented vertically, and you can see the stirrup. Let me show you how the stirrup works. I think that suppose I start from here. Let me ask you, can this beam fail into two parts without snapping the stirrup? Look at the stirrup. The stirrups are going from the bottom to the top hang on the stirrup hanger, those in green. Now, if this crack is to open, can it simply fail without snapping the stirrups?
No.
No, you have to, the stirrups must be snapped for this beam to fail. And that's what increases the shear capacity. Why is that? Because you can see those stirrup will go all the way, will hang on from the stirrup hanger. And if you want to simply fail the beam, you have to simply tear all those rebar here. I'm gonna show you where we tear the rebars. Okay, like along the crack. And that's why stirrup, they increase the shear capacity, because not only you have to fill this uncracked portion of the concrete, but also you have to tear apart all the stirrups to fill this beam in shear. Okay, so guys, I mean, it's not very difficult, by the way. Like, you will understand how much. I mean, I'll give you the logic behind this equation here. So this will be our final equation here for VS, but I'll explain for you how. There is a very good question to ask you right now, and I think I should give you some mark for it if you answer it. So guys, the beam, now we discuss the shear resistance. So the beam itself, the concrete beam, is in shear. But I'm asking you, is my stirrup in shear or something else?
Something
Are
else.
we shearing the stirrup? So we're shearing the beam. So yes, the answer is yes, the beam is in shear. But I'm not referring to the beam right now. I'm asking you for the stirrup. The stirrup is in shear. And by the way, you should answer this question very nicely because you're doing steel. Are those stirrup in shear or something else? Show your hands, please, if you know the answer. Martin?
They're in something else. It's not shear because they're being stretched.
Okay. Okay, I'll take this answer, Gord, what do you think? Is it in shear?
I was gonna say pretty much the same thing, and possibly that it's more compression than shear, but
Okay, so we have Jelly. What do you think, Jelly? Is it my stirrup, like the stirrups are in shear, or something else?
I think it's in share because based on your share formula, it says VC plus VR, VC plus VS. So share is considered is also part of that sharing stress.
I think you didn't get my question, Jelly, but anybody else has a contribution like to this? My question is this, Yes, my beam is in shear, but I'm asking you the shear force on the beam. Does it cause shear on the stirrup or cause some other stresses on the stirrup? Okay, Martin, I'll go back to you one more time. So you thought that there is not shear. So what else could be?
Axial force. I think that's the name of it.
Yeah, but axial force, like Gord said, compression. Do you
Yeah,
agree with Gord? It should be compression or
tension.
huh?
It's in tension, is it not?
It is intention. I will give you the full mark, and I will give Gord the partial mark. So yes, guys, need to think about it. So Gord, you got 2 marks. 2 marks, and Martin, you get 4 marks. So guys, please give yourself some time and try to understand. As I said here, look at this picture here. So yes, the beam is in shear. The beam is in shear. The concrete is in shear. However, the steer, look at this. So this part here is trying to pull down. This part here is trying to pull down, and it's hang it from here, hang it from the top, which means you're putting those stirrup in tension, okay? So all those stirrups are in tension, not in compression and not in shear. If you don't remember this, look at the steel connection. Did you guys study steel connections? Are you at this point or not yet?
Yeah, we
yet.
have still connection.
So on the steel connection, like you have 2 plates and they are held by
Bolts.
some bolts. And if
Yeah.
you put tension on the plates, what happened to the bolts? Are they still in tension or in shear? They will be in shear or maybe double shear if you know those names. So shear, think about what is shear. Think about shear. Probably I need to switch off my screen and just look at my screen here. So guys, here is the bar. If you're doing this, see my hand, this, it means it is tension. If I do this, it's compression, and both of them axial force. But if I do this, if I'm trying to shear the section, that's called shear. So the shear is perpendicular to my section. So for the stirrup, I'm asking you, for the stirrup, are we putting the stirrup in tension or shear one more time, Jelly? What do you think?
Um. No. It's intention, not in share.
Intention. Okay, so intention. And guys, this will make us our life very easy because I'm asking you now, if I give you a bar, a single bar, like in strength of material first year, okay? If I give you a bar that has a cross section, known cross section, okay? Can you anticipate what is the force that will fail the member if I tell you that the F field is 400? And what's the meaning of 400? 400, it means every square millimeter can take only 400 Newton, that's per millimeter square. And all you have to do is you multiply by the area. If you multiply the area multiplied by the stress, you're getting the force that will tear your section. And then finally, if you simply multiply by our resistance factor, which is reduction, so you can see here is the area. I'm going to call it for now AV, and I'll give you details of AV soon. And if you multiply it by F field, so this basically will give you the force that is required to fail a stirrup, okay? And then why do we use this phi S? Anybody still remember from day number 1 in my class, why do we multiply F field by 85%?
Because that's the value of the steel.
Yeah, but what's the concept? Why we reduce the F field?
To increase the resistance.
Actually, we decrease the resistance.
Decrease.
If we multiply by 85%, it means we're reducing the resistance. It's called the resistance factor or reduction factor, because we cannot guarantee that all my rebar will be at F field at 400. So sometimes because of the variation of the material, then we sometimes get less F field than the nominal F field. Okay? But the thing is, guys, look at this equation, how simple it is. You're just taking a stress, multiplying by area. So if you multiply stress or reduce the stress by area, what we're getting? We're getting a force. And this force, basically, this number here, if I, for example, this is 0.85 and this is 400, and let's say this is 100 mil. So if I multiply 400 by 100 by 0.85, what I'm getting the force that is going to fail this rebar. Okay, are you guys following so far?
Yes.
Yeah.
Okay, now I know that. Listen, so far the idea is super easy, but the question is, what is AV? So please be patient with AV, but AV is the area of a single stirrup, and I'll give you more details in a few minutes. So for now, this is the area of a single stirrup. Multiply by reduced stress, it means I'm gonna get the force that will fail a single stirrup. But the thing is, when I fail my stirrup, am I failing one stirrup or I'm failing many of them? Please look at this pictures, please. Look at this picture here. If I want to split this beam here, am I trying to fail one stirrup or I'm trying to fail more than one stirrup?
More than one.
More than one stirrup. So the question is how and how, or sorry, how many? So how many is very simple. It's based on the geometry. So look at the crack. So try to understand how many stirrup can go through the crack. It's very simple. If I assume that the distance between the stirrup from here to there, I'm going to call this one S, which is a spacing. So if I'm able to know this dimension from here to there, okay, I can simply tell how many stirrup they go through the crack. Are you guys following? I'm gonna say let's say call it X. If I'm able to know how much is my X, if I divide X by the S, then I will get how many stirrup I will need to break. Are you guys following?
Yes.
And that's exactly what's happening here. Okay, so you can see this part, you can see there is no invention. This part is the same as this part. So phi s multiplied by a sub v multiplied by F field, this is the force that simply fails one stirrup. So you can guess, what is this guy? What is this guy here? This is a number. This guy is a number. Number of what? Number of stirrup that crosses the shear crack. Okay? And it's not super science. It comes from the geometry. I'll show you here. So look at the geometry here. Okay? So look at the geometry. So this dimension here is dV. And if the angle of the crack is theta, you can imagine that this dimension from here to there, this is going to be d sub v cotan theta, which is x, huh? So this x here is going to be d sub v cotan theta. Why is that? Look at this angle here. So I'm going to draw for you guys the triangle, huh? So this one side here, and this another side here, okay? And this another side here. So if this vertical dimension is d sub v and this angle is theta, so the horizontal component using the trigonometry is going to be d sub v cotan theta. And if you divide by the spacing, then you get the number of stirrups going through that crack. And then all you have to do finally is multiply the force that can tear one stirrup by the number of stirrups. Guys, what you see on my screen, there is no super science. It's very, very basic. Do you guys agree or disagree?
Agree.
Take your time. If you cannot follow, take your time. The V sub S, which is the contribution of the stirrup to the shear, is nothing more than what is the force that can tear one stirrup, and then multiply this number by how many stirrups going through the shear crack, which this number comes from the geometry. Huh? So finally, guys, here is my final conclusion. And I'm gonna skip this. I'll come back to here, but let's go to this final conclusion here. Okay, so we said that my beam shear capacity, called the V sub R, has two components. V sub C, which is concrete, can take this much, and then this is called V sub S, which is this stirrup can this much. And in the code, you will see in the code there is something called the V sub P. And please, anytime you see V sub P in my lecture, in my slides, just ignore it, and I'll tell you why. V sub P is the pre-stressing effect. So you guys know that there's something called pre-stressed, huh? Pre-stressed concrete. I'm pretty sure you know that.
Yeah.
I'm pretty sure that you know pre-stressed concrete, huh?
Yeah,
Okay.
yeah.
So pre-stressing, we have a cable, and those cables, they take a curve inside your camera, your beam, and because they have an angle not horizontal, then in this case they have a component in the shear, in the vertical direction, huh? And that's why if your beam is pre-stressed, then there is a third component together with the stirrup, together with the concrete, that helps with the shear capacity. Am I teaching you anything in this class about pre-stressed?
No.
No, and because there is no pre-stressed here, all we do is cast in place like a normal concrete. Then please, anytime in my class you see V sub P, then ignore it because that's not going to be taught in my class. Okay? So in my class, the shear capacity of the beam has two components, concrete part and a steel part or stirrup part. And you can see there is no invention. Here is the concrete portion, and this is the stirrup portion. And then finally, we add them together, and this is our design equation. So what I'm going to do right now, I'll box this one for you because this will be our design equation going forward. Okay? Now, just something for sure all of you guys know, for my beam to survive the shear, for my beam to be safe in shear, this has to happen. And please, if you don't remember by now, or if you don't know by now what is the difference between those numbers, please understand the following. Anytime you see sub R, it means resistance, it means capacity, it means the maximum shear force that my beam can take. How about V sub F? V sub F is the shear capacity, the shear force,
Factor.
the factored shear force, or the shear force coming from factored load. So for example, this number can be 1,000. So it means my beam can take 1,000 kilonewton. Okay. This number on the right, it can be 900. Okay. It can be 800. Okay. It depends on how heavy my load is and what is my span and other things. But it can be any number. As long as this number is less than my capacity or the beam capacity for shear, then we're okay. And that's what we do in our design. In our design, we design our beam so that my VR is equal or more than my VF. Guys, the same discussion, we had it before when we talk about M. So the difference was M sub R has to be greater or equal than M sub F. Okay, so you can see if you put some effort in my class from the beginning, then by now it will pay you off because you already created good foundation for you. Okay, because there are lots of similarity between different designs. Now let's go back and see what is VF, and VF is kind of confusing part. In this equation here, we said A sub V. So in this equation here, we said A sub V. But I want you guys to understand what is A sub V. Let me look at this picture. So guys, look at this picture here. We said that the crack, this beam cannot fail before your stirrup is torn here, right? So the stirrup will have to be torn here and torn here. Would you agree or disagree?
Agree.
Now, let me ask you, is AV, let's say this stirrup is 10M stirrup. Let's say that this is a 10M stirrup, okay? I'm asking you, what is A sub V? We know by now. And please, if I ask you guys right now, if I take somebody randomly, let's see, because I got some information from other instructors that students, they don't know what is the area of 10M. So let me victimize some of you guys. I'm sorry. Otherwise, I will feel so disappointed. Let's look at somebody who is so quiet. Somebody probably Daniel Obia. Daniel.
Hi, sorry, I just go back from the restroom.
Okay, no problem. Daniel, if I may ask you, what is the cross-section area of a 10M bar? Would you know? $15M bar. Do you know the area of a $15M bar?
I don't know it's offered, but I have it on my book.
Okay, no problem. Would you get it from the book? Would you able to get it from the book?
Yes.
Yes, guys.
100.
The area of cross-section area of a 10M is 100 square mil. Okay, let me ask you guys. Let's go to here. If we were to fill this beam, are we tearing 100 millimeter square or something else?
You said AV is only for 1 bar, right?
No, I didn't say until now. I didn't say what is AV. I said that's area of stirrup. Okay, the area of the stirrup. But I'm asking you, look at this picture right now. We're saying here that those are hang. So those guys are hang from. Those guys are hang from here. Okay, and so those guys the same. This guys hang from here. And for our crack to open and beam to fail, we need to tear apart our stirrup at this point here. And I think everybody agrees. I'm asking you right now, when we multiply our phi s times F field, and that's reduced stress, should I multiply by 100 or something else? What is the
By
area
100.
exposed? What is the area exposed to the tensile stresses? Is it 100 or something else?
Isn't it
By
two?
100. By 100.
Only 100?
100 times 2.
100 times 2. That's correct, guys. That is, thank you, Nick. 100 times 2. Because we have 2 legs. We have 2 legs. And again, there is no more evidence and proof more than the 3D picture. Huh? There are 2 legs going through the crack. And we need to tear apart 100 on this side and 100 on this side. So 100 per leg, which means an AV is equal to 200. And it's here. I'm going to, if you look at my slides, I spent some time to come up with those beautiful cross sections to show you what is AV. So I gave you the first example on the left where it's a 10M stirrup, 10M stirrup, and 2 legs, which is most. I'll tell you guys, this is the most you will see in your life. If you're working on a condo building or something like that, mostly you will see very enough a 10M stirrup, 2 legs. But if you work in heavy construction, you will see we need more than that, like let's say a bridge girder or transfer slab, okay? But in general, look at this. So this beam on the left, we have 10M stirrup, and you can see I have 2 legs, which means I need to tear this leg. I need also to tear this leg, and it means my AV will be 2, and you can see, okay? Actually, I'm mistaken. I should have replaced those. It's supposed to be the opposite. I think I did this on the right side, but I'll correct this one and re-upload. So the 10M has 100 millimeter square. And you can see we have 2 legs, which means my AV here is equal to 200. So I need to multiply my 200 times F feed, which is 400, times 0.85. How about this side? What if you have a beam and the beam is so wide and it has a 15M stirrup, 15M stirrup, and the stirrup looks like so. Look at my screen, and sometimes we do that. So the stirrup has more than 1 leg, and you can see how many legs? We have 4 legs. So what will be the AV in this case? If my stirrup is 15M, by the same, from the same table, Daniel, 15M, the cross section is 200, and if you go multiply 200 times 4, so this will give you 800, which means my force will be 0.85, that's phi s, multiplied by F field, which is 400, and then finally multiply by 800. This will give you the force needs to be to tear 1, 2, 3, and then 4 bars. Guys, does it make sense for you? The AV is not the bar, the area of the bar diameter. It depends on how many legs. As I said, in general, normally we have 2 legs, but sometimes because we have heavy loads, we will need more than 2 legs. Okay? So that's AV. So we're done with AV. So let's go back to here. Now you know what is AV. Now, again, today I'm not going to give you, probably I don't have time to give you like a numerical example, but I want to finish all the theory behind stirrup. So let me show you shear reinforcement option. So what are the shear reinforcement option? In general, we call them shear reinforcement. And I said most commonly, we add stirrups. So what are the other options? Here we go. Number one, we have here a vertical stirrup, and I said here that's most common. So if you have done some, like if you have been to work sites and job sites, you will see this is the most common. So what we do is we add some bars and we add some vertical stirrup. This one here, it's only on the book. I have never seen anybody will do that, will simply make inclined stirrup. I know it's in what happens, those are more efficient because look at this. Where is the shear crack? Shear crack comes to an angle 45 degrees. And you can see, if you can see, my stirrup is perpendicular to the crack, which means it's more efficient, but practically, this is not practical to make those inclined stirrup. And if you guys have some experience, you will know why this is impractical. Okay. Now the third option is called bent bars. Bent bars. Where is the bent bar in this picture? So you can see here, this is my bent bar. Okay. So a bar that goes from the positive bending from the bottom at angle and then goes to the top, and that's called bent bar. And you can see, where is my shear crack? My shear crack goes this way. My shear cracks goes this way, and you can see the bar goes almost perpendicular to my shear crack. It means if you want to fail the beam, then you have to also tear those bars, bent bars. In Egypt, I've seen lots of bent bars, but in Canada here, it looks like needs some experience, and people they have problem reading the drawing. And this is not really a preferred option in Canada here. In Egypt, for a good reason, because they want to save some rebar, they use bent bars. But in Canada, it's not very popular because of the labor. Okay. And then finally,
I've only seen it a few times, Tahir. I've usually see the vertical stirrups. I've seen the bent bars a couple times, but I haven't seen any of the other ones with the welded wire or the angular.
100% agree. And I can tell you, even the designer who did those bent bars, I would say is adventurous. Like, like designer, when they did something, they have to consider the quality of our labor we have here. I can tell you how many times I've done some design and I know that I'm wasting some material, but I'm making less confusion on site. And this will make, because what happens if I'm trying to become so precise and make, whenever needed here, and then what happens, someone on site cannot read the drawing properly and switch them, put this somewhere here, so like switch them, put this many somewhere and those many somewhere. What happens? You have to simply waste a lot of time, a lot of money to take the rebar apart and then fix it. And that's why best way and safest way is trying as much as you can, try to unify your reinforcement, make it as much as you can close to each other or the same, if you can do that. And you can see here, if you look at my screen, for example, where those bent bar will start. Okay. So what happens if I start early or I start later? Is that okay? So I would say the engineer who did the design for those beams that you built, I would say is not really paying attention to the quality or the communication problem that we have here in Canada. As you said, the last option, which is welded wire mesh, is not really, it's just only on the book. So those pictures are coming from the book. And I can tell you, here we go. It is this 99% and this 1%. But nobody ever does this like the inclined stirrup, or nobody add welded wire mesh. Thank you so much for adding. Okay, guys, another detail here, which is you look at this picture and you will see what we do here is we come at the top and we simply make this guy here. What do we call this guy? Does anybody know what do we call this guy here?
A hook.
A hook, yeah. So guys, this hook here, it is not one thing. I'm going to give you some details or more details about the hook. So the hook can be either 90 degrees on the right. So this one here on the right here, it is 90 degrees. And why it's 90? Because this bar here was going to the vertical and then it was bent 90 degrees. And then how about this guy? That's called 135 degrees hock. And then the last one, it goes to 180 degrees. Let me ask you, which one you think is more robust? Which one anchors your bar into concrete? Remember, I want to remind you that this bar has a tension. The stirrup, this bar here, there is something trying to pull this bar down. And also here, we're trying to pull this bar down. And also here, we're trying to pull this bar down. And it looks like this bar has to be well anchored into your concrete. Otherwise, it will simply snap. Okay? I'm asking you guys, which one you think is more robust? The 90 or the 135 or the 180? Just feelings,
180.
180.
180 is the strongest hock. This one on the right, 90, it is very sensitive to the cover. So if you don't provide the appropriate cover, like when I say cover, I'm referring to this distance, from here to there. Okay. So if this distance is not really maintained, you will be in trouble. And that's why myself, I'm not recommending to anyone to use this kind of 90 degrees hock. Most commonly, we use 135 degrees. Remember, every hock comes with a minimum length. Every hock comes with a minimum length. You can see here, after the radius, you need to provide a straight length of 12 diameter of the bar. Okay. How about here for the 135 degrees? We need to provide, because it's stronger, so we need to provide less hock length, 6 diameter of the bar. And finally, here for 180 degrees hock, then it's only 4 the bar diameter. Now let me ask you, which bar? Am I referring to the diameter of this green or this red bar? What do you think?
The red bar.
Red bar. Thank you so much. Green has no business. The green is called stirrup hanger, and it's only meant to keep the stirrup in place. So here what we do is we go 4 times the diameter of the stirrup. But remember, there is a minimum distance, which is 65 mil. So no matter what you do here, you multiply, for example, 6 times 10. What do you think? 6 times 10. How much is that? 60. The minimum is 65, 2.5 inches. So no matter what you do here or you estimate, you must provide a minimum of 65 millimeter hook length after the radius, which means from this point to this point here. Okay. Now let me show you some stirrup detailing. Very important, Those discussions are not just like not important discussion. They are very important discussions. Okay. Now, those two, you will see those two are very, very common, very common stirrup detailing. Some detailers or some engineers, they design their stirrup to look like this, and some other engineer will design their stirrup to look like this. Okay. If you ask me what is your preferred method, I'll tell you the one on the right is my way to go, and I'll tell you why. The one, and I already gave you some like writing here. So the one on the left, it's assembly acceptable by the code. So the code allows this one on the left, and it saves material. If you compare between the one on the right and the left, which one has less material? Very easy, Which one has less material?
The one on the left.
For sure, because you're missing this side here, which is cross, So this one you're missing, which means, and if you think that you have to have a stirrup every 300 mil and you have the length of the beams on your building this much, you're saving a lot, okay? But I can tell you, even you save here some money for this material. This one here on the right, it provides an excellent cage. If you're making those as prefab, you bring them from somewhere and you drop them where they should be, then this makes a very good cage. And it wastes a little bit of material on the right, we know that. But the thing is, if you have torsion, and I'm not sure how many in this class know the meaning of torsion. So I put here a simple picture of what torsion is. So torsion is a moment, is not bending, So the torsion is a bending perpendicular to the center line of your beam. Same as my picture. Look up my picture here. This picture, guys, this is the meaning of torsion. If the beam has torsion, this on the left here is forbidden. If your beam subjected to torsion, this detail is forbidden. And which one should we do? We do the one on the right because it forms like a closed loop and it works in torsion. This one here, it doesn't do anything in torsion because we have kind of continuous stress around the beam. Okay. Now, how about, do we have other details? Yes, we do. I'm going to give you a few of them. So the one on the left, some designer will simply double the top. It provides a more anchorage. It provides a more anchorage, and it works fantastic in torsion. The one on the top, okay? And of course, we waste more material because you can see we're doubling those. So we have this leg here and this leg here, so we're doubling material here. So again, this is still acceptable by the code. It makes a good cage, and it's preferred in torsion, but it wastes some material. How about this one? Have you ever worked on project that has this detail here and try to know what's going on, huh? So what happens here? You're making two U bars. We call them U bar. Did you work in any project that has two U bars?
I've not seen any U bars.
I tell you, I work on one project and it works mainly if you have a very deep beam. So sometimes our beam will be 1.5 meter deep, like 6 feet deep. If you have a deep beam, always the contractor asking for this. We, as a designer, we start from this and give them this on the drawing, and they ask us if we can simply replace it by this. You know why? Because it's super easy to build. If you have some experience, you'll know what I mean. That if you have two two inverted U shape, is very simple to build, because what you do is you put the bottom ones, you put the bottom rebar, and then next to what you do is you put the top rebar, and then you close it with the U bar. The only problem with this one here, remember that the stirrup is in tension, huh? The stirrup is in tension. So this guy's trying to pull down. And remember, we're hanging everything from the stirrup hanger. So which means what? Which means that we need to provide here splice length. So we need to get enough distance along which my force will simply transfer from this leg to this leg here until you get the force to the top. And that's sometimes scary. Sometimes people that are not paying attention, and if you don't provide tension splice length, you're done. It doesn't work at all in shear. Okay, last one. The last one is this one here. I make it in clear in red, and I say this is forbidden. If you put here only one U bar, you're done, because simply this bar here will simply get out of your concrete, like snap out, because there is no anchorage, huh? So the rebar is not anchored into concrete because we don't have any hook at the very end. So 90 is okay, but it's very sensitive. It's not recommended. 135 or 180, but without any hook, you're done. Are you guys following so far?
Yes.
Then let's take a break. Okay, let's take a break. We'll see you guys 2:05. Thank you.